in an extraordinary milestone that pushes the limits of human achievement. NASA's Voyager 2 spacecraft, launched in 1977, has once again reshaped our understanding of space. Now more than 12 billion miles from Earth, Voyager 2 has crossed beyond the heliosphere, the vast bubble of particles and magnetic fields created by the Sun, and entered the unknown expanse of interstellar space. What it has found at this distant frontier, where the Sun's influence fades and the galaxy begins, is nothing short of astonishing. The information streaming back from Voyager paints a picture of this cosmic boundary as far more intricate and unpredictable than scientists had ever imagined. This isn't just another milestone in heliophysics. It's a profound shift in how we understand our solar system's place in the galaxy. The discoveries made during its crossing of the heliopause, the boundary marking the edge of the heliosphere, have appended decades of theoretical models. Rather than a smooth and gradual transition, Voyager 2 revealed surprising and often bewildering phenomena that challenge existing science. Voyager 2's journey itself is epic. Launched on August 20th, 1977, was originally tasked with exploring the outer planets, conducting historic flybys of Jupiter, Saturn, Uranus, and Neptune. Once its primary mission was completed, it pressed on, powered by a radioisotope thermoelectric generator that converts the heat of decaying plutonium into electricity. Despite its 1970s technology, Voyager 2 has survived the extreme conditions of deep space for nearly half a century, traveling at speeds over 34,000 miles per hour. On November 5, 2018, it crossed the heliopause at a distance of 119 astronomical units, roughly 11 billion miles from the Sun, becoming only the second human-made object, after its twin Voyager 1, to reach interstellar space. But unlike Voyager 1, Voyager 2 still had a functioning plasma science instrument, offering a rare opportunity to study this transition in unprecedented detail. As Voyager 2 breached the heliopause, it began to detect anomalies that baffled scientists. The boundary was expected to be a relatively smooth region where the solar wind, a stream of charged particles from the Sun, gives way to the interstellar medium, a sparse mixture of plasma and magnetic fields between stars. Scientists anticipated a gradual decrease in solar particle density, a weakening of the Sun's magnetic field, and a rise in cosmic rays' high energy particles from supernova and other distant cosmic events. But what Voyager 2 encountered was anything but gradual or simple. Its instruments recorded dramatic and irregular surges in cosmic ray intensity, rather than smooth, consistent increases. The rays came in pulsating waves with strange patterned rhythms, suggesting that some unseen forces or structures were influencing their behavior. Even more surprising was what the magnetometer found. The magnetic field beyond the heliopause was not chaotic as predicted, but highly ordered and nearly 3 times stronger than what Voyager 1 had observed. Even more intriguingly, the field was aligned in the same direction as the one inside the heliosphere. This consistency between the two spacecraft, separated by years and billions of miles, suggests that the transition between solar and interstellar space may be shaped by larger, coherent galactic forces. These revelations challenge the long-standing assumption that the heliopause is a diffuse, passive boundary. Instead, it may be a sharply defined and structured frontier, one that reflects active interactions between our solar system and the galaxy beyond. Voyager 2's plasma science data added further complexity. Inside the heliosphere, plasma tends to be hot and diffuse due to the solar wind. In contrast, interstellar plasma was expected to be colder and denser. But the spacecraft found a surprising in-between state, plasma that was denser than the solar wind, yet cooler than anticipated. For interstellar space, this hints at a transitional layer, a sort of cosmic buffer zone that may separate the heliosphere from the broader galaxy. Just before and after the crossing, Voyager detected a slight increase in plasma density, followed by a sharp drop. In solar wind particles, it wasn't just a change in quantity, it was a shift in the very nature of the plasma, defying both solar and interstellar expectations. As Voyager 2 sent back radio signals across the abyss of space, scientists noticed subtle frequency distortions. These shifts suggested that the signals were passing through complex Plasma structures beads and folds that resemble currents in a turbulent ocean. These weren't random disturbances. They appeared to form coherent patterns, possibly shaped by large-scale magnetic or electric fields. This indicated that the heliopause isn't a quiet threshold, it's a dynamic, turbulent region where solar and galactic forces collide and reshape each other in unpredictable ways. Among the most surprising discoveries were magnetic reconnection events. These sudden explosive realignments of magnetic field lines release intense bursts of energy, usually observed in extreme environments like the vicinity of stars or black holes. Yet Voyager 2 recorded these events far from any known stellar body. Its magnetometer detected rapid changes in magnetic polarity and accompanying spikes in particle energy, proving that even in the supposed calm of interstellar space, powerful electromagnetic forces are at work. Even more intriguing was the directional asymmetry in cosmic ray detections. Instead of arriving evenly from all directions, these high-energy particles were coming from a specific region of space. This suggests that something, possibly a magnetic filament or gravitational structure, is guiding or deflecting them. Like a lens-bending light. Some scientists believe this could be a magnetic wake created by our solar system's movement through the galaxy, or evidence of vast, stable galactic magnetic structures that alter the paths of particles across light years. These findings have deep implications. For decades, the heliopause was seen as a distinct boundary marking the sun's reach. Voyager 2's data tells a different story. The heliopause is more like a semi-permeable membrane, interacting with its environment and constantly changing. It acts as a shield, deflecting much of the cosmic radiation that would otherwise reach Earth. But it isn't static. Its shape and effectiveness fluctuate with solar and galactic activity. As our solar system drifts through different regions of the Milky Way through magnetic clouds, gas densities, or even dark matter, the heliopause could shift, potentially exposing our planet to increased radiation. Over geological timescales, such changes may have influenced climate, evolution, or even mass extinctions. Voyager 2 also detected a hybrid plasma state, neither fully solar nor interstellar. This mysterious form may represent a new phase of matter found only in transitional zones between star systems. It might also serve as a chemical crucible, where reactions produce complex molecules, possibly including precursors to life. If these reactions are occurring at the boundary of our solar system, they could reshape our theories on how and where life's building blocks are formed. Additionally, the spacecraft recorded coherent low-frequency tones described as plasma quakes, suggesting that the interstellar medium can support standing waves or resonances. Much like a musical instrument's string, this implies the galaxy may have an acoustic or electromagnetic structure capable of transmitting energy and information across immense distances. Voyager 2's instruments also picked up unexpected chemical signatures, negatively charged oxygen, ions, as well as traces of iron and nickel at energies suggesting origins in ancient supernova. These ions, likely carried by galactic winds, highlight the outer solar system as a melting pot enriched by stellar remnants. Dust grains detected in interstellar space were smaller, more irregular, and possibly coated with organic material or frozen gases interacting with the plasma and magnetic fields to produce signals Voyager 2 could detect. This dust-plasma interaction may help us understand how planetary systems form, or even how life's ingredients are seeded across the cosmos. Another fascinating observation was the detection of shockwave, caused ripples in particle density, in magnetic fields that appear to be remnants of past solar events like flares or coronal mass ejections. These echoes, arriving years after the original events, suggest that interstellar space acts like a resonant chamber, preserving and reshaping waves of energy over vast distances. Voyager 2 also revealed that the heliopause itself isn't uniform. It's asymmetric, compressed in some areas, stretched in others, suggesting it's being shaped by external pressures, perhaps from interstellar shock fronts or magnetic anomalies. Strangely, this lopsidedness doesn't align with the galactic plane or the sun's motion, hinting at influences we don't yet understand. Some speculate that we may be passing through a wave of interstellar gas, perhaps a ripple caused by ancient gravitational shifts, or even filaments of dark matter, which could subtly warp space and fields in ways still beyond our measurement. Capabilities: the spacecraft also recorded sharp, localized temperature changes, abrupt rises and falls over small distances, indicating the presence of boundary layers or miniature shock fronts, akin to atmospheric weather fronts. This suggests that the outer solar system is filled with a form of complex space, whether that may pose hazards to future spacecraft or astronauts who venture beyond the heliosphere. Voyager 2 even found evidence of anisotropic turbulence energy, moving preferentially in certain directions, like sheets or pulses, instead of smooth flows.